Can everybody hear me okay? Okay, so we're going to get underway. So at the end of last class, we started to talk about testing. Remember I drew this pyramid where I said you're going to need some system level tests, test the entire system the way an end user would. You need some unit tests, you need a lot of those, and you can have some things in the middle. They're like in unit tests, but they're a bit bigger. They test more of your program. We call those integration tests. You should have some of each of these things. So you know how to write system level tests, where you test the whole system. That's what you've been doing to date in 105, 244. How do we write these unit tests? So our goal with unit tests is to test individual classes or functions, or sometimes a few of them working together, but basically a smaller part of my program. Okay, so how do I do this? So one way is maybe I can carefully choose my user input so that it's going to just test a little bit of my program. Okay, so I'm going to have somebody enter, or maybe I'll capture to a file some input. It's going to go into my program. And what I really want to test in this unit test is some low-level class. So let's say it's a class that stores a point, an X and a Y, and has some operators. Check if 2 points are equal and so on. We actually have a class like that in the graphics API we're going to give you for milestone 2. So I want to actually check if this point class works in one of my tests. Can I just choose user input so that I make sure that if the point class works, it passes. If the point class works, it doesn't pass. What do you think? Is this a good way to make a unit test? Anybody want to just... This is like a 50-50 chance. Actually, F12, I'm assuming you buzzed in on purpose. I'm going to call on you. So F12, what do you think? Is it a good idea or bad idea?
That was by accident.
You did it by accident. Okay, but you know what? I'm going to call on you anyway. It was a happy accident. So this is very fortuitous. So what do you think about my technique to make unit tests? So I'm just going to carefully choose my user input to try to get the program in the right state to test this one class. I think it's a good way to make a unit test.
It's a what?
Practical way to make a unit test.
The unit test should be general.
It should be what?
General, so you can use it for multiple different cases.
Yeah, it would be good to be able to do this for multiple different cases. So you're not liking this too much, right? Is that correct? Yeah, it's not going to work. So this isn't how you make unit tests. You don't try to carefully craft your user input and then carefully measure output. Why not? Basically, you don't have enough control this way. Right? This is how you do system level tests. Sending some input into my program, I don't know that I've gotten this point class into the right state to check maybe the equality operator. It's very hard for me to know that I'm for sure checking that. And also, in particular, it's impossible for me to know that I'm only checking that. I've gone through the whole program. If something's broken, my test is going to fail. I want my unit tests, when they fail, to point me in a much more localized part of my program. So I just can't do this. This isn't how you do unit tests. So what do you do for unit tests instead? Well, you actually write code. Okay, so you're not just capturing inputs into a file and saying send this through just like it was an end user typing it. No, you write code, and that code puts your class or maybe a part of your function, a part of your program into the right state. But let's just think of a class as a good example. And then that code can also just directly call methods of that class. And you can immediately check what it gets back and say whether it's good or not. So this is called a test driver. Okay, code to check other code. Okay, what does this look like? So let's do a concrete example. So here's a little piece of code that I wrote. I really needed my program, and it makes this two-dimensional point. Okay, so X and Y, and I can do things like multiply my X and Y coordinate by some number. So I've got a multiplication operator, a times equals operator, and some other stuff in this class. Okay, so I would like a unit test I want my unit test to test little bits of functionality so that when they fail, it's really obvious where I should go look. So I made a function here called test point times that all I wanted to do is check that this times equal operator works for my class point. So how do I do that? Well, I make one of these point objects. Okay, I set x equals 1, y equals 2 with this constructor. I call the times equal operator, so I say let's multiply that point by 3. and then I check, did I get the right answer? So I know exactly what it should be. It should be x equals 3, y equals 6. So I check, was this equal to the expected output, a point of 3 and 6? And if it isn't, I print something out. I say test 1 failed. Maybe I could print a little more out, say how it failed or something. And the convention in unit tests and tests in general is that functions that have errors return how many errors. So I had 1 error, so I returned the number 1. Okay, if I didn't go into this if statement, it means that everything was good, right? I did get the point 3, 6, which is my expected value, so I return 0. So I don't print any output, and I return 0 saying that there were no failed tests. So by convention with tests, they tend to be silent if they passed, and they return 0. If they fail, they give you some information, and they return how many failures. Okay, so this is now code that will never ship to an end user. It is only to test other code that I've written. So in order to run my unit tests, I actually need to compile my program a little differently. What I do is I have a main function, okay? So we can only have one main function in any program. So here I've got a main function that is just going to run unit tests. It's not interesting or useful to an end user at all. This is just for developers. So it basically says the number of errors is 0, and then it says increment the number of errors by whatever came from this test point time routine. And normally in your unit tests, what you'll have is a whole bunch more tests. Okay, usually your main program won't just have one test, you might put a whole bunch of tests in there. So you might call a bunch of them in sequence, and at the very end, we'll print out how many errors there were. Okay, so this will never ship to an end user either, right? That's a different main function for our program. The program we build with that main function doesn't do anything any user would want. It just tests things. Okay, and now we basically have a couple different ways to build our program. So let's say this is my real code. My code.cpp is actual useful code that I'm going to put in my program. So let's say my whole program is pretty simple. All it is this my code.cpp file, and I have a main file. Those two files together make my real program, say some little graphics application. So you know from 244 I can compile that with G++, and you say -o says what's the output name, so I'll say it's program.exe. This is what I'm going to sell. When I'm doing tests, I build my program differently. So I use G++ again. I compile this code, mycode.cpp again, because that's the code I'm going to test. But now I also compile in this tester.cpp file, where I've written tests, and I compile in this test main file that has a main function that only invokes tests. And I normally give the output of that compilation a different name, so I'm going to call that test.exe to make sure I don't get confused and accidentally ship that to my user base. Okay, so does this make sense? It's a bit different than 105 and 244. We can actually now build our code in multiple ways. One way that we're going to send to the end user, one way that is just going to run unit tests. Okay, so that's what we're doing in milestone 1. In milestone 1, your file organization is this. You've got a directory called mapper. It's under ece297/work, and that's where your whole project is. Underneath that mapper directory, there is a libstreetmap directory, and underneath that is a source directory. That's where all your code is being written. You write as many files as you want in there. We gave you m1.cpp, a little skeleton to get you going, but you can make more. When we compile your project, so you make or you hit the rebuild button in your IDE, all of that code in that libstreetmap source directory gets built into what's called a library, and the library is called libstreetmap. Okay, a library is just a collection of .o files. So you can think of this as a whole bunch of .o files like main.o, myhelper.o, etc. Whatever CPP files you have, they all get compiled into .o files, and then basically those .o files are put together, technically linked together, into a library, and libraries end in .a. So it's basically a bundle of object files. It's bigger than an object file, but it is not a complete program. You can't, if you actually try to run this library by itself, Linux will say, that's not a program. That's not an executable file. You can't run it. Okay, so that's where most of your code goes. You also have this /main/source directory, and you can write code in there. We give you a skeleton of a main.cpp file, but you can write other ones. For milestone 1, you're not going to write anything in there. We don't care what you put in there. We're not going to test it. But that code actually turns into your mapper program, which is what an end user will run. And in milestone 2, that's what your TA is going to run. This is your functionality that is fun and exciting, but we don't care about it yet. Okay, so probably you can write things in here if you want. Sometimes students write some things because they like to do it for testing, but you don't have to write anything in there for milestone 1. And then the last directory here is this /test directory underneath libstreetmap. And these are the extra files that are intended, they just test other functions. Okay, these are the unit tests. When you compile these files, they make a different executable. So not mapper, they make an executable program called test libstreetmap. And test libstreetmap, all it wants to do is call your functions in your library. So executables can call into libraries. So it's going to call into the libstreetmap library. It's going to make sure your functions work. And just to make things convenient, we have another way that the unit test can be run, which is you just type the command ece297 exercise. All that command does is behind the scenes, it is basically building this and automatically running it for you and summarizing the results. So, okay, so you're going to run ece297 exercise a lot. And as you saw in tutorial 4, when things go wrong, you probably have to debug them. When you want to debug them, you can go look at our unit tests. They're all readable. And if you want to copy them into this directory, you can use ece297 exercise and the debug tester option. And it'll basically copy over the source code that we've written for some tests so you can actually run the debugger on it. Okay, any questions on that? Every year there are some students who kind of get confused about, well, wait, what's a mapper, what's a test libstreetmap? So hopefully everybody here now understands. This is the typical way that larger programs are tested. Okay, so if you go look at our tests, you'll find that there's a lot of repetitive code. So when you write unit tests, you write a lot of code to set up the test, check if the test passed, run all the tests, print out some messages, and give statistics. So you can write all that code by yourself. It's just C++ code. But because it tends to be kind of similar in different programs, there are things called unit test frameworks which kind of make this less tedious. So what are they? They're macros, which is this hashtag define, functions, classes, so basically constructs in C++ that have been pre-written to simplify coding. We're using a particular unit test framework called Unit Test++. It's a fairly powerful unit test framework. It lets us do things while writing less code, but it's fairly easy to learn. If you want to learn more about how it works, you read our quick start guide on it. And there are a bunch of different unit test frameworks for C++. There are also unit test frameworks for every other language you can think of. You know, the exact details of how they call things are different, but the fundamental way they operate is basically the same. So once you know how one unit test framework works, you'll be pretty, it'll be pretty rapid for you to learn another one. Okay, so how do they help us? Well, if you look inside of our code, you'll see that there are these capital test macros and test fixture. Those are setting up the state of the program, getting ready for a test. We will call your functions, then we'll call check to see if your output matches what we expected. So that's another thing the unit test is providing us with. There's a function called run all tests. It just runs all the tests. And outputting messages and statistics is automatic. It's just kind of handled by these other routines. So if you look at our unit tests, you'll see calls to these things, which are provided by the unit test library or framework, and they're not magic. They just basically generate C++ code. Okay, so when you're testing, the philosophy you should have is to be very paranoid. So you should assume anything that, well, there's two mindsets you should have. You create some new code or some new feature or some new design, you should assume it doesn't work until you test it. Okay, so it's just broken until you verify it works. Once it's passing your tests, you go, okay, well, it mostly works. But you should still be paranoid before you ship this out to the end customers that works when you test it quickly. But before you send it out to the world to use, you want to be more paranoid, saying, okay, let's start thinking about every possible way this can fail, and make sure we have tests or fallback behavior for each of those. So I think a good case study in this is the 737 MAX. So how many people have heard of the 737 MAX airliner, right? So probably many of you have flown on it. So yeah, it's had a troubled history. It's back in the news again because you saw that what they call a door plug, a removed emergency exit, came out at 15,000 feet and the plane depressurized, and if people hadn't been wearing their seatbelts, some people might have been sucked out. So that's a recent quality problem. Before that, though, it had even worse quality problems. So it had 2 crashes that caused a total of 346 deaths that were preventable, right? They were due to design flaws. And this article is in the Globe and Mail. It's behind a paywall. So if you have a Globe and Mail subscription, you can get it. If you want to read it and you can't get it, I can probably put a PDF on Quercus without getting involved in litigation. So send me an email. But let me summarize what this article says. So they had multiple design and test failures. So the first failure was the 737 MAX. It's very expensive to design a new airliner. Okay, so instead of designing a completely new airliner, to take advantage of the new, larger, more efficient engines that can be built. So there are jet engines that are much more efficient now than they used to be, about 20% more efficient, but they're larger. So one way you can deploy those is design an entirely new airplane where basically you move the wings up, you shift where the wings are on the fuselage, and the larger engines fit. So Boeing didn't want to do that because it takes literally many billions of dollars and many years, and they didn't want to fall behind their competitors, and they didn't want to spend that amount of money. So what they did instead is they put larger engines on their existing 737 fuselage. They didn't move the wings. So this is a smaller change, but now the engines basically had to be mounted where they're further forward than they should be. They're basically not at a point where they're aerodynamically stable. It's not where you would ever put engines if you were designing an airliner from scratch. So what they did is they used automatic control. Okay, so sensors to detect what's going on, and software control to interpret the pilot controls and stabilize the plane. Okay, so adjust the aerodynamic surfaces so that it is stable. It appears the engines are in a different spot than they are. And that system to stabilize it was called the MCAS. And it's a mix of sensors, software, control systems. Okay, so their first mistake was this is actually very shocking, they had a single point of failure. They had one sensor that detected basically the angle of attack and airspeed. I forget the precise metrics they were measuring, but 2 of the things they have to watch for is where is the nose of the plane and what's the airspeed. If the plane starts going up too much and loses airspeed, it'll stall. It means it loses lift, it falls out of the sky. So they have to watch for that. And they had a sensor to detect that, but they only had one. And yeah, this is shocking. There was an option to get a second one, okay? But it was like you had to pay extra as an airline to get like the backup sensor. So that's the first thing you shouldn't do, okay? You're building a system, especially if it's safety critical, you should not have a single point of failure. You have to assume everything that can fail will eventually fail. The second thing they did is they had a flaw in their testing. They did not test this software system that would basically change the control surfaces to stabilize the plane with a broken sensor. It worked fine if the sensors were working fine, but if a sensor was broken and basically was telling it like the wrong angle of attack, the system went crazy, okay? And they never tested that case. They didn't see what happened with the software. Their next failure was that basically to save money for the airlines that buy this plane, it's expensive to recertify pilots on a new airplane. So Boeing said and convinced the regulators, this is not very different than our prior 737s. You don't need to recertify pilots. You don't need them to go through extensive training. It can be fast. It can be done on an iPad in a day. And they actually kind of minimized the differences from the previous 737s in their documentation to support that. Okay, so that was not paranoid enough. And what it resulted in is when this sensor gave the wrong reason and the plane basically started fighting the pilot, right, trying to aggressively adjust the angle of attack in the wrong way, the pilots didn't know what was going on, okay, because they hadn't been trained on what could happen and it wasn't easy to find in the documentation. Why would this happen? How would I shut the system off? Okay, and then underneath this, there was also a cultural failure. So the cultural failure was that when they dug into this, they found many Boeing engineers were very uncomfortable with how this was being done, and they felt safety was being compromised for sales. But there was a lot of money on the line. There's a lot of pressure from the top of the company to make this project work on time, to not require pilots to be recertified, et cetera. So safety was compromised for sales. Okay, so obviously this is a tragedy. It has not worked out well for Boeing either. I mean, in the end, these crashes and the grounding of the plane, the damage to their reputation, as well, obviously, as the tragedy of killing many people has been terrible for the company. So this is not something that, this is a failure across the board. So I guess my point in this is first, just think about this when you're making systems. Don't have single points of failure, be paranoid. I could put up lots of different examples about this, of systems that failed and killed people, so it's something you have to think about as an engineer, is that, as you move out of school, you will build systems that people rely on, and you have to keep in mind how can I make this as safe as possible? And these overlapping layers of test and safety is part of how you do that. But I want to talk too about this cultural failure, because this isn't purely a technical problem, right? You can sometimes be pushed to do things that are risky. So what do you do in that case? Okay, so I want you to take a couple of minutes. We'll see how the discussion is going. If you guys are discussing really interesting stuff, maybe we'll go a little longer. And what I want you to do is, the people at your table, discuss if you were on the Boeing 737 project and you were getting nervous about these lapses, these risk factors in their testing, what would you have done? And the context is, management really wants us to go forward, okay? There was pressure from the sales part of the company, from the top of the company, make this work. So what would you do to draw attention to these issues? Okay, so let's take at least a couple minutes on this. some teams to buzz in and give us their thoughts. I think this is a really interesting one to think about. I was talking to a couple teams up there, so if you can quiet down now, we're going to talk now as a large group. For most of you, this will probably happen at some point in your career. I can think of a few times in my career where I've been in situations like this, and I don't think I'm atypical. So it won't probably happen, hopefully not very often, but for most of you, this is probably not a situation you'll never experience. So it's worth thinking about. Hopefully that makes you want to participate. If that wasn't enough, I brought a whole bunch of chocolate bars. If you like basically weigh in, participate, come down afterwards and see me. Okay, so E06, what do you think? What would you do?
So I think it's really dependent on like the situation of like how many people are aware of this. Like, so if there's like a whole team of engineers who are like, hey, we all think this is not a great idea, then I think it's really important to sort of make a really strong case. Whereas if it's just one person, I think it's more a matter of expressing that concern, and at the very least, if everybody says, you know, we think it's bad, you'll have some sort of documented evidence that says, you know, I thought it was bad, and this is my sort of recommendation to fix it.
Okay, so you said a lot of good ideas there. So the first thing is be open and speak up, which is harder than you think, okay? So, you know, when there's pressure from management, there's pressure from the sales team, it can take some courage to speak up, but it's the right thing to do, right? This is your job. So be open, speak up. You also said, you know, basically talk to other engineers. So you're kind of making them aware of it. You're saying, what do you think? Is this safe? Can we make this more safe? You know, basically you're spreading awareness, and you're also seeing if it's a general issue. Right? So you are concerned, and you're doing some background research to see, do others share your concerns? Can they allay your concerns? But, you know, in this case, they didn't. So your concerns are not allayed. Now, what do you do next? So I'm going to get D08. Can I get you guys just to quiet down? Okay, so you've talked to others, you figured out it's a broad-based concern, you're very concerned, management's not making you happy, but they're also haven't really listened to you. So what did you do next? I think you already alluded to it a bit.
Yeah, so it definitely is important to sort of formally document everything, and then like make a more formal, I guess, certain claim, or a formal claim that says, like, you know, I think this is bad, I'm raising this claim with, you know, higher authority, and then if it's really bad, you could even potentially go to some form of like consumer media to be like, or like a whistleblower of sorts, and be like, this is really not great.
Yeah, these are great ideas. Okay, so media, whistleblower. So yeah, great thoughts. I'm going to go to another team. We'll come back to these. I've got a few notes on the next slide. So A09. Go ahead.
Yeah, I mean, there's also like another subtle approach to this. You can, you know, like create complications, or like tell the higher ups, those that are responsible for decision making, of the existence of complications, which would slow down the developing process, and hopefully they would be able to, you know, with time and through like insistence, they might even drop off the project altogether if the you know, the problems outweigh the benefits.
Yeah. Yeah, that makes sense. So I've captured that as escalate to higher management, right? So you're usually talking to your team, you're talking to your immediate manager. So all good points. So I'm going to go over to Professor Chong. Professor Chong, what do you think? What would you do? Let me see if I think I got to turn your mic on. Sorry, I've not done this well. And I think we have a few things, yeah, so maybe this helps with the, well, actually, I'll let you talk about it first, and then we'll write down some notes. What do you think? Is there anything that we didn't capture here?
The mic is on. Okay, great. I think you captured a lot of things. I think the main thing is to document the concerns in some sort of way, whether that is internally within the organization, or if you have to go out to the media and to kind of make use of that whistleblower law. But definitely documentation is really important, because if anything goes wrong, that documentation will be looked at very closely.
Yeah, so that makes sense. So I actually like the way I guess the students have come up with this too, because you kind of have an escalation here, and that's the right way to do this. Okay, so you start, you're concerned, you're gathering information, you're talking to your peers, you're talking to your immediate management, but they're not taking it seriously enough in your opinion. So you start escalating. You're documenting. But first, maybe you weren't documenting that carefully. You're just making presentations to lay things out. Now you're documenting to make sure, as Professor Chong said, there's a trail, because we have to escalate further. The other thing it does is as you document, it starts, sometimes in a company, people don't want to see documents when they know they're doing something that is not good. Okay, so the act of documenting can also force sort of better behavior. You can escalate higher in management. Take some courage to do that, right? You escalated higher in management, people don't want to hear it sometimes. But that is your job, to have courage. And you can even go to whistleblower organizations, the media. Obviously don't do that first, right? Because what if these are things that are going to have repercussions on your career, and that doesn't mean you don't do them. It means you try to resolve it other ways first. That gives you more credibility as a whistleblower. It also means that something that's going to be a difficult step is not the first thing you do. It's something you do when you really have to. So we kind of captured a few thoughts that Professor Chong and I wrote down in advance of this. So what are the problems? So first, the technical, okay? So they didn't have enough testing. They needed a more clear test plan. They needed overlapping tests, right? So they had software and single centers that could fail and could take the plane out. They didn't have a pilot training. They didn't have multiple layers. They weren't paranoid enough. So that's the technical. This should have been fixed. But there was clearly more than just technical factors at play. There was this desire to minimize change and the perception of change in this aircraft. And that's where this needed to be flagged to management. If it's not addressed, it has to become stronger language in writing where you're going on the record. So you can talk to your management initially just verbally, right, with just a feeling. Then you get data, and then you start sending emails, right? They're written, they're documents. In every company, they retain emails on servers. They're legally obliged to do this, okay? Altera had a policy of all emails are kept for 6 years. After that point, they can delete them. Why? Because if you're ever sued, they image all the hard drives, and I was involved in a lawsuit when I was at Altera, so I know this, right? I didn't do anything personally wrong, but just companies sue each other. So companies can do things like say, we delete all emails after 6 years, but they can't just say we just delete them at random, because that's not keeping records that could be relevant in a lawsuit. What does that mean? It means you send an email to your management or your upper management that says, I'm concerned about safety, and here's the reasons why. They know that's on the record. Okay, so they would prefer you talk to them first, probably a good idea, but they're not listening. This is escalating it, because they know if something goes wrong, there's a paper trail that one of our engineers said this was not right. It does require some courage. They're not going to be super happy about it. And then, as Professor Chong said, you can go to whistleblower legislation. There are tools, you can look them up. It takes even more courage. It has negative consequences on your career, but I've never had to do this. Hopefully none of you will. It's good to be aware this exists. It exists for a reason, to prevent, horrible behaviors. So I said that you'll probably face things like this in your career. I haven't faced this very often, but I have a few times. So I can think of one particular case where there was a bug in Quartus. Some of you might have hit bugs in Quartus, but this was a bad one. It was a bug in what's called the timing model. The timing model says how fast the chip will be. So one of our Cyclone family chips, we had a bug in it. It was one of the teams reporting to me that put the bug in, by accident. When we make a new chip, a new FPGA comes out. For a while, the timing is marked as preliminary, means we can change it. But then at a certain point, we've got enough data, we've tested enough chips, we say it's final. We won't change it without telling the customers. And it means customers can ship their product with confidence. So it's a big deal to say we have to change something after we said we were done. My team said, look, it's a bug. We have to fix it. It can result in major errors in how fast the chip is. Doesn't happen that often. Only happens about 2% of the time. But when it does, could be a major error. And so it was obvious to me we had to fix it. But basically, the head of our customer and marketing, the whole customer-facing part of the company did not want to do this, okay? So they said, no, it's only 2%. You don't have to worry about 2%. It's our decision. We're not telling people. We're not doing it. And I tried to, it got escalated by my team to me. I tried to explain it to them why we had to do this. They just were not going to do it. So, and I actually started losing sleep over it because I was thinking, well, what if our chips go in planes, they go in surgery robots, they go in MRI machines, what if they fail? Like some of these failures are much worse than a video game crashing. So I just woke up one morning and when I know what to do, I'm not doing this. So I basically told my team, change the software, and I sent an email to basically the head of the customer-facing part of the company saying to ship our software with a known bug of this magnitude would be reckless. I will not do it. We're changing it. I will not change it back. So they could have overruled me. I mean, they could have gone, the head of marketing can't. They would have to go to the CEO and try to overrule me. But that's incredibly risky now. I've said I won't do it. I'm going to resign first, and I've used words like reckless, which have legal meaning. So they didn't try, right? And so sometimes you have to do this. This was actually a happy ending. We fixed it. It was the right thing to do. But if I had just kind of gone, a bunch of people really don't want me to do this, I'll just go along, we would never have changed it. Sometimes in your career, you will probably have to just do things that make people unhappy. It's hard to know when the right time to do that is, but it may happen to you. Okay, so testing tools. So that was ethics, but now I'll go back to kind of the mechanics of testing. So what tools do we use for testing? So see tutorial 4. We're going to use the debugger. So we can, and I use it not just to find bugs. I actually, new code, I step through it in the debugger to watch it execute to make sure it does exactly what I expect. So it's kind of like preemptive debugging. Memory checker. So if your program's ever behaving very strangely, run the debug check build, run valgrind. You want to find memory corruption problems right away because you can't reason about a program that has memory corruption. And there are other tools, so both those you're going to use in this course. There's another set of tools we won't use called code coverage. What those code coverage tools do is you run all your tests, and they keep track of how many times every line of code in your program is executed. So let's say I have this little function, right? It's got an if statement in it, and let's say this is my only unit test, okay? I call my function just with an input parameter of 8. If I do that, it's never going to hit this line, right? This line only gets hit if input is 0, and I have no tests that check that. A code coverage tool will tell me that. It'd say that your tests cover 6 out of 7 lines, or 86% of your code, and this particular line no test covers. So that tells me I should go make another unit test. I should make sure it covers that line. I was visiting friends at Google a few years ago, and when I went to the washroom, this was on the inside of the stall door, right? They have every week, they would change the little tutorial on testing that you would see in the washroom. So they put them on the inside of the cubicles in the washroom because they thought, well, this is like a communication challenge, right? People are busy, how can we communicate to them good test practices? And it came about because a group of engineers at Google felt that Google was losing some of its really high quality software engineering heritage, and they thought as they were growing, and how could they improve it? So they had to educate people, and they're busy people. So I actually had an interesting solution to the communication challenge. We're going to put it 1-minute tutorials on the inside of the toilet cubicles, and each one taught you something interesting about testing. That's relevant because it shows how important testing is, right? So Google takes it very seriously. They want people to be good at it. You want your testing to be and your building to be very automatic. So you want to make it really easy to do the right thing. So in ece297, you'll notice that there's one command, make, or in your IDE, you can click a build button. That builds your whole project. There's one command to test it all, and there's one command to submit it all. And that's on purpose. If you ever actually go read some of these things, you'll see that some of the scripts you're running are actually hundreds, even thousands of lines long with all the things they do. We don't want to show any of that complexity to you. We want it all automated. At Google, they do all those things as well. Very easy to build, very easy to test their code, but they go one step farther. They make it easy to deploy. So again, with a very simple command, they can basically send a new code change to their website and they can split the traffic so that a fraction of users get the new code. And they call that an A/B test. So this is a new level of testing. They're actually deploying it to live traffic, and they can see, well, you know, not just that it's stable, but does it work better? Does it getting better response metrics? And then they have other tools that if it's not working out well, they can reverse it quickly. They can stop sending traffic to that deployment. So one of my friends at Google, he was in the ads division. So this is the ads division basically makes the little auctions that are deciding what ads show up beside your search. And this is where Google makes most of its money. Okay, so there's an algorithm to figure out who's going to pay the most for this ad based on whether you're likely to click on it, how much they're going to pay, et cetera. And he made a change to that one day, or he worked on it for a while, he deployed a change, it worked well. He actually, it made Google an additional $50 million, which sounds great. Another week, he made a different change. He deployed it to the website. It took 2% of the traffic. It didn't work that well. You know, before he pulled the plug, it had already cost several $1 million. But he saw it wasn't working well. He pulled the plug. So it's pretty interesting. You know, they kind of push this beyond continuous integration into continuous deployment, and they make mistakes doing that. It's part of what makes them agile, but they can pull back the mistakes quickly. In order to do this kind of continuous deployment where you can send something out to live traffic, you know, quite quickly, you need really good automated tests, okay? So Google has really good testing. Okay, so we've got a few minutes. I'm going to talk about coding style. Well, any questions about testing? All right, so software engineers tend to go, I don't like testing, I like writing code, but testing's super important, don't neglect it. Yeah, ece297.
How do we, what's the command for doing the line testing that you were talking about?
The unit testing or what?
No, the testing in which it checks whether a part of the code was executed.
Oh, code coverage? We didn't build you code coverage tools for this. So there are a bunch of them, but we're not using them in this course. Because in this course, we decided we would write the tests for you because it was just too much to give you long specifications and have you try to write all the tests. Okay. So testing is important, but we're kind of just embedding you in a good test infrastructure. Later in your career, you will have to make sure you set one of these up.
Yeah.
Okay, so I'm going to quickly, sorry, go ahead. Yeah.
So like for this milestone, would the tests that are given to us be enough, or should we do like more?
So the public tests test most things. We have private tests to make sure you don't just hard code all the answers. They're no harder. We will leave some corner cases out, okay? So you read the header files, they talk about corner cases. We will test a corner case if we list it there, okay? Will we test it in the public test cases? Some of them we're not going to test in the public test cases. So we're checking, did you actually read the header file?
I see.
Does that make sense? Yeah. So basic functionality will all be tested, but some corner cases are for sure not in the public test cases.
Okay.
Okay?
Yeah.
Okay, so we took quickly about good coding style. You'll be graded on this through this course, and it's an important thing for your whole career. So what do you think of this code? Just a little piece of loops and so on. So what do you think of this? Don't worry about what it does. You have an immediate reaction. Good, bad. What's your first? Okay, so I see D11 giving it the thumbs down, which in the Roman Empire means, you know, execute this one. So you think this code should be destroyed. Okay, so what do you not like about this code?
I think it's okay, but it's kind of bad. I can understand what it's, because it's a simple program, but I feel like the indentation is really bad.
Yeah, so the indentation is terrible. I mean, I don't have indentation. So this is like rule 0. Indent your code properly. So indent it obviously for every loop, every if statement. Also use some blank lines between functions and so on. This is like punctuation. If you don't do this, it's like handing in an English essay where you didn't capitalize the start of the sentence and you don't have any periods or commas, right? Like, you can't imagine how enraged your English professor will be, right? Don't do that. Okay, so really basic. Okay, so this one, I'm going to give you a minute. I want you to read this code. Tell me what it does. If you get it right, I'm giving you a chocolate bar. So when you think you know what this code is, you can put up your hand and tell me, and I'll call on you first. Actually, better than your hand. If you know what it is, buzz in. I'll call on you first. Okay, anybody want to take a shot at it? Okay, E03, what does it do? For the potential chocolate bar, where are you? Go ahead.
Like, does that take like an integral or?
Okay, that's good. It is an integral. Can you tell me a little more about it though? There are many integrals.
Oh.
I'm still going to give you a chocolate bar. You got enough. But okay, so anybody want to, we got that it's an integral. Anybody want to like fill in any more blanks? Last chance. Okay, it's definitely yours. Chocolate bar. How about this? Okay, let me put this up for a minute. Maybe we don't even need a minute for this one. Buzz in if you know what it does, okay? I'll take you in order. So as soon as you think you know what it does, it has to be you have to add more detail than what we already have, but if you can add some more detail, you can do it. F06 you cleared out. Does that mean you don't know what it does, or is that an accident? Yes? What's that? Okay, so I'm going to put this back on. Okay, so F06, you looked like you wanted to take a shot at it. Do you know what it does? You could, yeah.
Does it just calculate the definite integral
Of what? Okay, you were close, but I'm not taking the. So, okay, anybody else get it? Okay, what do you think? Okay, so it's E06. What do you think it is?
Is it just the integral of the area of a triangle?
It's an integral of a triangle, sort of. It's a function, right?
Yeah.